Quantum computing is a revolutionary technology that is transforming the future of computation. Today we'll look at how these machines work and their implications for the future. But first, let's dive into the history of how they came to fruition. In 1936, Alan Turing presented the idea of a universal machine, a machine capable of computing anything, laying the foundation for classical computers. Initially, computers relied on physical switches to represent bits, according to an article by the Quantum Insider in 2020. This was then changed to transistors in the 1950s, making them smaller and more efficient. The introduction of integrated circuits in the 1960s enabled even further miniaturization. As chips and transistors shrank, quantum mechanical effects began disrupting traditional computing designs. Finally, in 1982, Richard Feynman had a vision of a quantum computer that could simulate quantum systems through the concept of qubits.
The fundamental component of all computing is the bit, where each bit can either represent 1 or 0. Quantum computing has its own twist on the bit with the qubit. Instead of 2 bits just holding 2 pieces of information, 2 qubits of information hold 4 pieces of information. This is because qubits hold information based on the total probability of all the states of the qubits. All the different combinations of qubits are called superpositions, which are all simultaneously true until observed. For a supercomputer to be possible, these qubits need to be able to have their states be controlled and stable. In quantum physics, we are currently having trouble keeping the qubits stable and not changing state. The qubits need to be completely isolated from the outside world, which is currently impossible with modern technology. Scientists have come up with the idea of having extra error-correcting qubits to correct for any qubits that switch on accident. But another solution currently is to use quasi-particles, which are particles that don't interact with the environment as much as normal particles. Currently, the most common type of quasi-particle is the photon, but there are many more. So now understanding the basics of quantum computing, what are the future implications of quantum computing?
One of the most frightening impacts of quantum computing is it has the potential to crack encryption codes much faster than a modern computer. Encryption is the process of converting data into a code that only authorized users can access. Modern computers would take many years to crack encryption codes, while quantum computers are capable of cracking them in just seconds. This poses considerable risks as hackers could quickly gain access to sensitive data. On the other hand, quantum computing will have a tremendous beneficial impact on a variety of fields. Pharmaceutical companies are exploring how quantum simulations can reveal new drug possibilities by analyzing molecular structures. In a 2019 publication to the MIT Technology Review, Giles says companies like Volkswagen, Daimler, and Airbus use quantum simulations to enhance battery efficiency in electric vehicles and calculate fuel-saving routes for aircrafts. Quantum computing is also an invaluable tool in energy efficiency, financial modeling, and even accelerating artificial intelligence. While quantum computers are incredible, they won't replace the everyday computers we rely on. Quantum computers are built on qubits, which are highly error-prone and unsuitable for many computing tasks. It may take years to fully address these technical obstacles, and even after these obstacles are addressed, classical computers will remain essential for general computing needs. Quantum computing may still be in its early stages, but it has the potential to revolutionize fields like cryptography, medicine, and AI. As advancements continue, we're only scratching the surface of what quantum technology can achieve. Thanks for joining us on this journey into the quantum realm.